Hello everyone, I'm Gael Glorian and I will talk about the dungeon variation problem. This work has been supported by the Nouvelle-Aquitaine region and is a collaboration between the worldwide video game company Ubisoft and the library. First, I will introduce the problem and our motivation for this work. As a top video game company, Ubisoft aims to create AAA+ open world game. Creating such massive games requires a lot of content, which cannot easily be done, at least at this scale solely by human collaborators. The main objective of Ubisoft is the player experience, who needs to feel free and have a lot of different actions in this gigantic world. To offer complex gaming experiences, we need to fill worlds with coherent dungeons. How can we do that? By using source dungeons. These source dungeons are templates created by level designers. By combining constraint programming and design intents, it allows us to generate a lot of coherent variation of the source dungeons to be placed into the open world. Our main objectives are to provide a tool exploiting CP to help generate sets of level variations and guarantee that the variations are of the highest quality. We can formally define the dungeon variation problem as follows. Generate an appropriate variation of the source dungeon by deactivating a subset of initial rooms and corridors such that the remaining set of rooms matches a given set of constraints. The terms room and corridors are for simplicity's sake. Indeed, you can generate a room as a set of rooms, another dungeon, a city, and so on. The same applies for corridors. It can be doors, vents, road, etc. Here's an example of two variations used in production. In this graph, the nodes represent the rooms and the edges represent the corridors. The blue node marks the entries and exits. In this case, the node 0 is both. The black nodes and edges are the ones kept into the variation of the source dungeon. You can see that both belong to the same source dungeon. Here, the same graphs as before, but only with the rooms and corridors that belong to the variations. It allows level designers to express their needs in terms of narration, difficulty, exploration, or encounters. For clarity's sake, we did not show the orientation of the edges. In the left variation, we can see that there is a main path with two shortcuts or optional exploration, whereas in the right one, we can imagine a treasure chest in room 10, a boss fight in room 18, and a locked door from node 18 to 0, for example. In this part, we present the constraints we propose to guarantee the consistency of the generated variations. We do not explain the model globally. You can refer to the full paper for more detailed information. The objective of the Connected Plus constraint is to ensure that the generated variations do not contain disjoint dungeons and that they are playable. This means the dungeon should not block the player and all rooms are accessible in at least one possible path. To achieve this, the constraint is split in two distinct parts, the connected one and the path one. Keep in mind that we are working with directed graph with cycles and no clearly defined main path. Moreover, we can have several entries and exits in the dungeons and can also be the same node. In practice, this happens when an entry is a door or a destructed wall, for example. To avoid distinct dungeons inside one variation, we explore the graph starting from any node of the graph that is still active in the search. All the nodes we encounter during the DFS is marked as seen. Notice that in this part of the Connected Plus constraint, we go through the graph without considering the orientation of the edges. If all decided active nodes are seen during the DFS, then the graph is not disjoint and we can then filter unseen nodes. The second part of the constraint used to ensure the playability of the dungeon uses a similar algorithm. The main differences are the starting points and that we now consider the orientation of the edges. Indeed, we go through the graph from each entry street active and we mark the nodes encountered. When handling a node in order to validate a path, we need to check if the node is an exit or belongs to an already validated path. If this is the case, we can validate the path used to get to the current node. The search is not stopped when a path is found valid. Indeed, we do not only want to check if the exits are attainable, but to validate every node accessible. When this algorithm ends, if all decided active nodes are marked, we can filter unmarked nodes, which are thus unreachable or blocking. Let's illustrate the algorithm with an example. Here we have a dungeon composed of 8 nodes and 13 edges. We have 2 entries, node A and G, and 1 exit, node B. Obviously, this graph is not disjoint to only show the path part of the connected plus constraint. The nodes and corridors in the example are all still active. Node H is filtered by the model constraints. We start from node A, a still active entry, and check if it's already validated or an exit. This is not the case here, we thus move to one of its child. Continuing on node B, we do the same checking. Here, B is an exit. We can validate the path used to go from node A to B. We move on node E, do the checking. We then go back to node B, the first child of E, and validate the path since B is valid and also an exit. We then consider node F. Node F will be validated thanks to the path to node B. And we move on, checking node C. As we can see, nodes C and D are blocking. They will be processed and won't be validated. After backtracking to node A, we can validate the edge from node A to node F. Nothing more can be explored from entry A. We move on to entry node G. Entry node G is validated because it is connected to node F. The algorithm ends and we filter nodes C and D since they were not validated. In order to validate our method, we did some experiments. They are divided into 3 parts. The 1000 dungeons experiment to show the practical interest of our approach. Then, an experiment on a real-world dungeon, and in the last part, we present a dungeon generator based on Rath-Strogat's model, in order to evaluate our methods and its scaling on bigger pool of instances. The 1000 dungeon experiment's objective is to show the usefulness of our approach in the industrial context. Indeed, being able to generate a lot of valid variation quickly allows us to painlessly fill a world with different variation. We can also imagine training bots for exploration, fight, or debugging matters. In our example, we generated 1000 dungeons from 3 source patterns with the following configuration: between 3 and 12 rooms, at most 3 final rooms, final meaning that they are dead ends, 1 treasure in a final room, and between 3 and 8 fights. To avoid close variations, we use a simple method. We computed 50,000 variations and took one every 50 solutions. In the perspectives, we will see that there is a lot of improvement possible on this point, and we plan to rank variation in the future. Here's a sneak peek of the generated dungeons. We can distinguish the 3 different source dungeons in the figure. The next part is divided into 1 experiment on a real dungeon and 1 on generated ones. This is the experimental protocol we used. The connected plus global constraint was implemented into NACR solver with an alternative XSP3 parser kindly provided by the team to handle connected plus constraint in XSP3 models. The experiments were run on a 6-core Int'l processor with 32 GB of RAM. The timeout was set at 2400 seconds. We compare our method with the same model without the global constraint connected plus. The real dungeon instance is representative of the majority of real instances we have to handle. It is composed of 52 nodes, 58 edges, 7 possible entries, exits, and final rooms. The corresponding XSP3 instance have about 3000 variables and 11,000 constraints. As told before, we compare our method, connected plus in the table, with the same model without the global constraint, without GC in the table. We tried to generate 100, 1000 and 10,000 variations with the two methods. In the table, we display the CPU time to compute those variations, the number of conflicts encountered and the number of variations that are valid. The validating process is done a posteriori and the time is not taken into account. We can see on the table that the overhead of using the connected plus constraint is rather small compared to the ratio of valid variations. Indeed, with connected plus constraints, you only compute valid variations. In comparison, to compute 100 valid variations without the connected plus constraint, we need to compute more than 5,000 solutions. And to compute 1000, we hit the timeout with less than 300 valid variations. We cannot conclude the interest of our method on this unique real instance. This is why we propose a dungeon generator based on the Watts-Strogatz model. It allows us to generate graphs with small world properties and to simulate real instances thanks to high clustering. It works as follows. We constrain the wing lattice and change the destination of edges according to probabilities. We use this generator, the link is available in the paper, to compute 100 instances from 10 to 100 nodes with a step of 10. Here are the results obtained of the generating instances. This confirms the interest of our approach and the limited overhead. Indeed, the median CPU time is similar between the two methods, but ours computes only valid variation. To conclude, we introduced the dungeon variation problem and proposed a XSP3 model. To tackle the problem we faced, we introduced the connected plus global constraint and show the practical interest of this method on generated and real instances. We also demonstrate the industrial interest with the 1000 dungeon experiment. A lot of perspectives emerged from this work. We could do an optimization version of the dungeon variation problem by using metrics to rank the variation. Some metrics already exist in the video game state of the art, such as map linearity, path redundancy, leniency, and mission linearity. We could also rank the possible paths inside a source dungeon or a variation using data or estimates on time to complete rooms or difficulty to do so. There is a lot of possibility to enrich the model by adding more parameters on room and connections. Moreover, we could handle distance constraints to constrain the length of the different paths of the variations. A more distant perspective could be to consider QCN to move rooms in space. To finish, our long-term objective is to be able to generate high-quality levels on the fly based on user experience and with strong guarantees. Thank you very much for your attention.